Hello, people. Welcome to week 11. You've all obviously, week 10 was the midterm week, and I do believe that was 2 Mondays ago. And of course, we've had problems. I mean, this is media site. Here we are again. It was offline for about a week. I didn't trust it. Yesterday it was back. I didn't trust it. I had to wait 24 hours to see that it's stable because two times I had tried to record when it was unstable. And one time I spent an hour and a half and the whole thing was corrupted. So I started putting things on YouTube. So now I'm just going to post these on both YouTube and Media Site in case this happens again. So let's talk about the midterm. All right, let's just go to that midterm. So these questions, you've had them all. That was in a PowerPoint. What's the significance of this? And that's that n factorial always dominates 2 to the n. So a factorial dominates an exponential. In this case, for all n greater than or equal to 4. All right, so this is the proof. Asymptotic dominance of factorial or exponential. That's very important. It would have been important for chapter 3, that's for sure, but we didn't cover chapter 3. We moved functions into the chapter we just finished. Pascal's identity, both algebraically, this is trivial, just that by the definition of these binomial coefficients. And you just, in place of nk, you put n minus 1, k minus 1, and all of the definitions. That's what this is. This is this term. This is that term. We did this in class already. And also a very simple combinatorial proof. So you can prove this by, this argument that we went through already. It's almost an element argument method, but not really. Here, this was interesting. So state the recursive definition of Fibonacci sequence. Well, that's it right there. And next, consider the sum of each successive sequence of increasing n and sum these terms. That would be these 1, 2, 4, 7, 12, a whole new sequence. And so conjecture that sequence. And well, we do that here. First of all, we suggest that it looks like 12 is 3. I forgot how it works. Okay. Well, anyway, this thing equals this guy plus this guy right here, 12, obviously. But how you guess the sequence is by noting that this term and that term equals 7. This term and that term, this term equals 4. It's just by looking at the patterns of how these numbers come. Okay, 7 comes about from, we were missing F7 in order to do that. So 4 comes about again by adding 2 to 2. So it's this to this, and this one is this to this. You can see that pattern if we extended it further. That's how we guessed that this was the sequence. So it's not a Fibonacci sequence with big F. See, this is actually terrible. This is not done properly. Oh, well, no, it is. This is the recursive definition of a Fibonacci sequence. But yeah, okay, so we use big Fs over here for Fibonacci. It's consistent. So we went through this in class already, or we suggested something like this in class. You first tackle the, this is way too small. You clearly P1 is true. P1 fits this no matter what. This is for n greater than or equal to 1. So P1 is true if you just stick it in here. Then you continue on to this thing that we conjectured, f of k plus 2 minus 1 plus f of k plus 1. So it's exactly what I just said in this ordering. It's conjecturing this set of examples of relations to that and so forth. But by the definite Fibonacci numbers, we have this fk. So we've got it all up to k plus 2 and k plus 1, but k plus 2 plus k plus 1 equals k plus 3. Hence, we have as required that all of these, okay, equal fk plus 3 minus 1 by the Fibonacci sequence. So this was worth maybe a point, I suppose, that you remember what a recursive definition is. It has to start with the initial conditions. This one is a second order recursive relation. And yes, that's that. Now this is repetition with, combination with repetition. We've been through this already. I did this one for you in class as well as a special topic. And that's it. That is it. We covered that all in class, and there's no reason to spend any more time on them. I've got something else here. Come on, that's not what I want. Okay, all right, yes. What do I want? Yes, okay. Oh my God, why is it doing this? Okay, what? All right. Okay, I hit the wrong button. There's where we left off last week. Okay, this was supposed to last all the way through from week 9 to week 10 because it's a very long presentation on functions. Relations. And I thought I'd space it out since the midterm happened recently during this process. And you were really, after a midterm, you're not that anxious to read the material. I get that. But now you're getting ready for the final exam. I went through this very quickly because I didn't have the document camera, which I do now. Yes, there it is. I have it now because this thing is back. We have the definition. Remember, in order to solve all these problems, know the definitions. Know the definition of a Fibonacci sequence. Know the definition of a function. Remember that it's if you have two sets, A and B, one is the domain, the other is the codomain, and within that codomain is a range, which is what this function maps to. So that has to be a relation such that every single element in the domain is mapped from exactly once. That's a function. That's all it takes. And, this is it right here. This sums it up. This visually sums up what these things are. Make sure you know, what they call this surjective, and injective, and bijective. The different classifications. That was cardinality. I asked you to memorize. I didn't go through this with you because I introduced the idea of composite relations, or composite functions. F of g of x is what that says. F of g of x. All right. So know this proof. I don't mean, so this is very important. If A maps to B is invertible, it is invertible if and only if it is a one-to-one and onto, okay, like a one-to-one correspondence. Obviously, that's true because you have to be able to map A to B, A1 to B1, A2 to B2, A3 to B3, and only have those one-to-one relations that can be reversed. Then you have an inverse function. You can't have any stray points that aren't involved with this one-to-one correspondence. So memorize that. That's on the test. That's on the final. You people, I'm giving it to you. It's just like with the midterm I gave it. I'm very lenient in this. I have to be, really easygoing on these online courses, these synchronous courses, because, well, they're different. We're testing out for the math courses next semester. I'm doing compute. What is it? 210 probability, which is an excellent course. The material is fantastic. Cardinality of functions. Well, it's clear. We just did a simple permutations with repetition argument here. It's just using the product rule. And then we have all these things. And so one-to-one is injective, onto is surjective, and one-to-one correspondence is bijective. Know this, please. Okay, and you can figure out if something's injective by the definition. So here, this is the proof I want you to know. Uh-huh. Okay, and this is the definition of a function being injective. So you have to test, and there's, for example, the rule of f of x squared equals x squared defines a mapping from the set of real numbers to the set of real numbers, which is not injective since it sometimes maps two inputs to the same output, 2 and minus 2, for real numbers. For integers, positive integers, or natural numbers, this would work. All right. Okay, we did this for onto functions as well. It turned out to be propositions, permutations without repetition. And that's just really easy to figure out. We went through this already. And onto functions involved Stirling numbers. So onto basically says you can map. Well, first of all, this whole thing, f of a, if you map all of this and it equals b, then it is onto. Okay, you can't have anything missing. Like this function here could be one-to-one. Every element has a one-to-one mapping to every element in this subset. But f of a equals b is onto. So you would map all of this to all of this. That's what an onto function looks like. So here's another example of how to figure out if something's surjective or not. Counting, this we went through a very long discussion of how we derived this situation right here, cardinality onto functions. You can't have these constant functions, and so this uses the rule of subtraction, that's inclusion exclusion. We have to exclude these when we count all the possible permutations, and that's all the possible permutations: 1, 1, 2, 1, 2, 1, 1, 1, 1, 1, 2, 1, 2, 1. You see how that works? This is 2, 1, 1. The next one. There we go. This is just simple counting. And for onto, we can't have this situation. That would mean in our beautiful little map here, that would mean this situation is true. That dotted line is the boundary of the codomain, of the range. That's the range. So when the range equals the codomain, that's when you have an onto function. Another way of putting it. So we generalized, never mind, we just went through all this and talking about overcounting again. And we generalized this. This is for this n equals 4. And we generalized to find this relationship right here. These two are the same. It's just that you've got a shift in the index. All that's happened here is a shift in the index, n minus k to the m. So here you're going 0 to n minus 1. Here you're going from 0 to n, which is the same. Okay, it makes no difference. And so we showed here, by plugging in the numbers, what the cardinality is. And then there are these questions. Never mind these questions. And so here's the summary of surjective functions. This is this is another way of counting onto functions by partition theory. Well, we haven't really studied that. Those that have an idea or have been exposed to partition theory, it's a subject of set theory, which we did not study in great detail. So this is, something you don't need to know for an exam. But it's illustrative and good for those that maybe have read or have been exposed to partition theory. This is a really nice formula or equality. And here is the discussion. It forces you to understand what a Stirling function is. Okay? You are responsible for this. You were responsible for this just like you were responsible for that other combinatoric argument equation that I had you do sort of out of the blue. So you're responsible for this. Make sure you know how to do this. This is going to be on the final exam. I'm being fair, telling you what's coming. All right. We didn't do any of these exercises. So, current tab. Before I go into graph theory, let me do this. So here's essentially a nice summary I got from ChatGPT, which I'm going to give to you. And I didn't check it for errors. ChatGPT is about 20% error prone. So you people, sorry, you individuals, or whatever you want to be called, I'd like you to read through this whole thing and understand it here. This is about distributions. The first thing, case one, distinguishable objects into distinguishable boxes. And how was that done? It was done by the product rule. Then there's these examples you can look at. Case two, distinguishable objects into identical boxes. Well, that ended up being the Stirling function thing. That's the onto business. All right. Identical objects in distinguishable boxes, well, that's just the combinations with repetition formula. And identical objects into identical boxes we did not study because this requires partitions. Partition theory, once again, the idea of partitions comes along. You're not responsible for case four. We did not cover it. So go through this. If you find errors, and you report those errors to me, I will enhance your grade by 1 point. And that could make the difference between a C and a C+. So I put it on you. How many ways are there to distribute 12 identical candles to 5? Always children. It's always children. So safe. So we use, of course, this formula that we devised here in this case right here. The identical and distinguishable. Identical into distinguishable. Identical candles into distinguishable children. Obviously, you use that. At least one of them. How many ways are there 12 identical candles to 5 children if each child gets at least one? Well, here you have to do a little trickery. So obviously it's 12, like up here, minus 1 and 5 minus 1, because you have 1 out of the picture. This is a nice way of looking at it here. So these are these kinds of problems you might want to do. Just go through those examples. There's, I'm going to send this to you. And that's just all about, so this right here is about, all this is about is distributions. I'll post that for you. I mean, they're simple problems, but they're, I think, really nicely illustrative. So you should look at that. If it was a class, I'd ask you if there are any questions. So we have finished. I have an appointment in an hour. This is something unusual. I don't cover graph theory. I only introduce it because it's necessary when we talk about trees, because trees are graphs, a specific kind of graph, just like functions are a specific type of relation. So graph theory was discovered or invented by Euler, a couple hundred years ago. So this goes on to trees, and we talk about these various different things. So let me run you, let me show you why this is important. Tree example problems. Okay, so why are trees so important? So these are graphs that are trees, that is. Efficient routing and communication networks. Solution, optimize tree structures for load balancing. Okay, we'll learn how to do that. Or how about a file system? File systems are all based on tree structures. Actually, not really. Almost tree structures, but let's just assume that they're trees and that no two parts of it directly go to the same file. Then you need balanced trees. You have to have balanced trees. We'll study balanced trees. So that when you're looking for something, some goals are not much further away from other goals. Okay, it's got to be balanced so that the response time is rapid. Today we have such fast computers that this doesn't even matter. Decision trees. Business need to make data-driven decisions. Represent the problem as a decision tree. Hierarchical routing in networks. Okay, well, there's the idea of a spanning tree, which we'll cover, a load balanced tree, dynamic tree updates. I'm not going to do this. Organizational structures. I should have done this. Oh, I should not have done that. Maybe I should have done this. Yeah, it's better. We'll save that. So it's the same kind of problems everywhere. Okay, um, um, phylogenetic trees and biology, tree of life, tree of certain species, and so forth. So that's a good introduction, I would say. Where'd that thing go? How did I get rid of it? Doesn't matter. So, what is graph theory? The study of graphs. Informally, graphs are mathematical structures. So you know why we're headed for trees. Trees are very important. That's the main subject here. But I don't see how to teach trees unless you study graph theory first. They are mathematical structures used to model binary relations between elements given of a given set, so ordered pairs. And there's terminology here at Wikipedia. It's actually very good in Wikipedia, but I generally don't go there. So this was done in the 18th century, and it's called the Königsberg Bridge Problem. So here is Königsberg. Here are some rivers, and Königsberg asked the question, can I, if you can see my cursor, is there a way to cross each bridge exactly once and be able to return to where you started? Well, here, I can either go into this area or I go out of this area. I don't ever go back to this point right here. It's pretty obvious you can't, but he wanted to prove it. No, and let's see why. First, you make a schematic. That's a schematic of this. Then you forget about all the stuff that you don't need. You abstract away. We can abstract even further as a graph. Okay, so here the A is this area here. B is this area. That's D. No, B is in the middle. D is down here, and C is over here. So you can see right here that there are three bridges that get you into region C. Region A has two ways to get to B. Region A has two ways to get to B. Region D has two ways to get to B. You see what this is. It's just a graphical representation with nodes and edges. We've seen these things before. So now we're applying them to this particular subject. Can one trace this graph starting at and ending at the same point without lifting the pencil from the paper, traversing each edge exactly once? So, this is some tree terminology. Look it up yourself. I'm going to get into it in the presentation on trees again. The reason why this is messy is because it's inconsistent in the literature. There's just so much inconsistency in what a path is, what a simple path is, these kinds of things. So I've got my list of things here, but you can't really read it. I'm just giving it as an example. Later on, you will see. So begin at vertex. I'll give you specific examples. We'll probably have to go with Rosen's definitions. Begin at vertex A. All right, that's here. Each time you pass through any other vertex, you use up two edges, arrive and depart, right? Depart and arrive. Okay. Thus, if it is possible to find such a route that uses all the edges of the graph and starts and ends at A, then the total number of arrival and departures from each vertex must be a multiple of 2. So now we call a point where edges are coming in. If there are several edges coming from several nodes, v sub I, we call that the degree. So for example, the degree of this node here is 3. The degree of this is 2. The degree of this is 5. The degree of deer is 3. So this is 3. I said 2. I was wrong. 3, 3. This here is 3 on C as well. So no, I'm sorry. It is 2. I'm sorry. A and D both have degree 2. So degree of B is 5, like we said. Degree of C equals degree of D equals 3. 5 plus 3 plus 3 is not even. That is such a simple way, and how graph theory developed, of solving this problem formally. Okay, there is no such root. So, definition of a graph is an ordered pair of disjoint sets, and that's the vertex set and the edge set. Vertex set and edge set, such that E is a subset of the set of unordered pairs of V. Okay, they're actually, in reality, Cartesian products. Graphs are formal mathematical structures. Okay, if G is a graph, then E is a function of G, the graph, is the edge set of G, and V equals is a function of G, is the vertex set of G. I don't know how that popped in there. Okay. Oh my God. Yes, I kind of messed this one up. I'll fix this when I give it to you. The definition of a graph. Yeah, I really messed this up. Okay, I've got to go and fix this. Well, judging by the time, I'll fix it. And tomorrow I will continue this and start trees. This is going to last this week and next week, as week 11 and 12. So I want week 13, the last week, to be review. I don't want to give you another section, which is chapter 13, I believe, which has to do with formal languages. That will probably overload this class. I don't want to do that. So far, we're doing fairly well. Yeah, I want people to do very well in the end. But let me just fix this and present it again from here. Okay. So with that, I will see you shortly. Au revoir, whatever it's called in